Good. So, what did we do in this course until now? Basically, we wrote a quantum field theory for the simplest case that one can consider, which was one-dimensional phonons. We actually even moved one step ahead. We got the case where we have mass, which doesn't exist usually for one-dimensional phonons. And we wrote down a solution. And the solution was something of the kind. Okay, I want to, before we're continuing on, I want to clarify a couple of small points regarding this solution. Basically, once I have n0, n1, n2, I can write down the energy of this solution. We saw it last time. Just to be precise, what are those K's?
Of what we saw?
Just the index.
What are those K's? Index is correct, but something more. If you remember, we did a Fourier transform, actually. What was our boundary conditions? They were cyclic boundary conditions. Meaning that if I'm writing down the values of K fully, not only the index, but the full, so it would be where L is the size of the system, and K can get any number, and this is something that I said, but I'm not sure that all of you paid attention.
Twice K, it's supposed to be N, no? K should be pi N, N.
So I'm using, I don't want to confuse it with N here. You want not to confuse it with this, so we'll put K tilde. And K tilde is a number 0, plus minus 1, plus minus 2, and so on. Why did I do it just here from 0, 1, 2? Just for convenience. Really, I should have also, after all these, written the solution for the minus. And what do they mean? What is the difference between plus and minus value in the K?
Is it like particle and antiparticle?
Much simpler. We'll get to an antiparticle today, I promise, but here we still, there's no yet antiphonon.
Because of the cyclic conditions, you go backwards if you take the minus.
Yes, and then you can move in this problem either clockwise or counterclockwise. And both are good solutions. Okay, so basically the solution is to tell how many energy quantas do I have at each value of K. That's the solution. Now, can someone tell me what is the dynamics of this solution? I wrote an eigenvalue, I have a Hamiltonian. It's actually a very nasty trick question. What do you know about eigenvalues in regular quantum mechanics? Eigenvalues of a Hamiltonian.
Energies.
Number.
The eigenvalues are energies. The eigenvalues are but what is the dynamics of the system? How does the wave function develop in time? Could you speak up, please?
I think it's I omega t. And then you put the omega on this side.
Well, correct, but it's just a phase. There's no dynamics here.
Okay.
Nothing. If I put the system here with one particle here, one quantum of energy, which I'll call a particle 3 here, 2 here, 0 here, and so forth, from here till eternity, as long as the Hamiltonian is only given by the Hamiltonians that I've shown you, nothing happens. It's in an eigenstate, and we know that an eigenstate of the energy, as long as there are no external forces or no interaction with other systems, remains in it. So, in some sense, it's the most boring solution you can have, but it's expected. We have here particles that we show don't interact. All you need to know is what's their K, and they stay in this K forever. All we know is that the energy is conserved and they stay in this energy forever. So what is the dynamics of the system? Nothing. If we want to have dynamics here, let's go think about our original system. If we have phonons, how do we get dynamics? How are phonons absorbed or created?
External energy.
External? Right. I have to send in a photon. I have to have them collide with an electron in the system. I have to have here some interaction with some additional system. But since we wrote only a Hamiltonian of one-dimensional phonons, which are non-interacting by construction, nothing happens here. Okay, so our goal in this lecture, hopefully we'll finish it in this lecture, if not the next one, is to start to write systems where we have some additional particles or some interaction in them, because otherwise life is very nice, it's easy to solve, but nothing happens here. Okay, and the other goal of this lecture is to give you a taste why symmetry is so important in field theory and advanced quantum mechanics. Okay, so we had our beloved Hamiltonian. Let's write it down here. So Hamiltonian density. what additional games can I play with this Hamiltonian or similar Hamiltonians to give me some richer physics? So the first game that we did was adding these terms that add a mass, a constant energy for each time that an energy quanta is added to the system. Okay, the next game that I can play with it is phi here is a scalar field. What does it mean, scalar? At each point x, we have one number, one real number. Okay, so that's a field. A field at the end of the day for each coordinate gives you a number, a scalar field, gives you a number. You're well aware that we have other fields. Please give me an example.
Vector field.
A vector field, electromagnetic field. For each point, I have a value of the electric field in x, y, and z direction. 3 numbers. Okay, so I'll start this game by treating a similar form of Hamiltonian, but for a field that has more than one number per coordinate. And I won't jump directly to 3 numbers. I'll move to the next logical continuation, 2 numbers. And because of convenience and beauty, actually, I write down these 2 numbers in a bit strange way for the beginning, but it will become very natural. Okay, so one way is to describe it as a vector. An additional way to describe a number with 2 components, what is it?
Spin.
Simpler.
A complex.
A complex number. So I'm dealing here with a complex field. Meaning that at each point I'm still one-dimensional. Why am I one-dimensional? Just for convenience. I could have gone back and do this whole exercise for 2 dimensions, 3 dimensions, 26 dimensions, whatever you want. Now I'll stay with 1 dimension, but with a complex field. So I'll call it phi, small phi in this case, just to separate it from the regular scalar field. And phi1 and phi2 are real numbers. So I have a good, well-defined complex field here. Write down the Lagrangian of this problem. Okay, so this term is very similar to this term, up to the constant that I threw out. this term is very similar to this term, again, without the constants. And I have here a phi square term similar to this. Okay, and now we'll spend a quarter of an hour on solving this Lagrangian with this Hamiltonian. Okay, to change it into a Hamiltonian, what do I do? The usual thing. I define the canonical variable conjugate to the field. And pay attention, I'm sometimes calling the derivative as dot t, sometimes dot. I'm doing it on purpose because different textbooks have different notations, and I don't want you to run into some notation and say, I've never seen it before. Okay. What is the only term that depends on phi dot?
First.
The first. Not surprising. And the Hamiltonian density will be okay. So far, so good, and the Hamiltonian, full Hamiltonian would be just I will just write it down, not prove all of it, but it's rather trivial. Someone could guess. Right, 0. Every time that I have the same operator at two different points, the commutation is 0. Which is also this case. Okay. The only interesting commutation relations would be between What will be this one?
0 and
0 again, because it's as if x1 with p2, a different variable has no connection for the same reason phi x. Okay. So, actually, one simple way to solve the Hamiltonian that appears here is to go back to its constituents, meaning phi 1 and phi 2, which are both real fields. Why is it easy? Because basically we did it before. So, I'll define just the two momenta fields will be phi 1. Just by the definitions. Taking the definitions and just writing them down. And I'll just directly write down the three components of the Hamiltonian. Nothing special, just writing down the definitions. Second term. Okay, and you can already guess that by fine. just again by the definitions. So my Hamiltonian okay. So what do we have here basically? Exactly our original Hamiltonian, but for two separate fields. How do I solve it? Exactly as I solved the previous one. I'll replace and end up with and define another operator. Okay, the total number of energy quantas in this system, and that will be a conserved quantity. Why? Because the same reasons that we for the same reasons that we started the lecture with. Nothing changes. If I put 5 particles of the first type in k equals 0, 2 at k equal 1, and so on and so forth, and the same for, and some other distribution for the second type of particle, will be conserved. And do you remember how I show that something is conserved in quantum mechanics? Commutation relation with the Hamiltonian. and either from physical understanding, the same arguments that we gave before, or going into it and doing the math. I have here N, I have here H. I know the commutation relations for A1K dagger and A1K the creation and destruction operators, and I can show that it's equal 0. Okay? Really? Nothing changed from this problem. The only thing that changed, I have two types of particles for the simple reason that I have a field with two components. There's an additional conservation in this system.
What is the conservation here? Of what? Of the number?
The total number of
Quantas.
quantas, or particles if you want, it's the same thing, remains constant because simply the eigenfunction doesn't have any dynamics. It stays the same. So the occupation stays the same, therefore nothing changes. If you want to be a bit more mathematical, you say that I write down here this relation, and I can go and do the commutation relation and show it explicitly. Not surprising, I can define an additional quantity, Q. Will that be conserved?
No reason it shouldn't.
Exactly, I have no coupling between phi 1 and phi 2. They can't move from one state to the other. So not only energy conservation, they can't move from one type of particle to the other one. I didn't give them any way to do it within this Hamiltonian, or in mathematical terms, again, trivial. But this will give it a really impressive name. This is basically charge conservation.
What makes it charge? Like in the physical equation.
At this point, nothing. Why? Because if I want really to call it charge in the physical meaning, I have to put here an electromagnetic field and show that it responds to an electric field in the way that you expect charge to respond to an electric field. So charge at the moment is just a name place. I'm putting a, what I can say is the meaning that if I have a given number of particles in the first field and a given number of particles in the second field, they won't transfer from one to the other, and that's conserved. Why I call it charge at the moment, it's not so clear. But I'll give you a bit of an intuition. Look, if I'm looking on the two fields here, they're completely symmetric, really. each term that I have at psi 1, I have the same term in psi 2. They behave the same, meaning that for the Hamiltonian without, let's say at the moment, an electric field, the two particles will behave completely the same. So perhaps it has some connection with charge, as long as I'm not putting in something that an electric field into the system. They both behave the same, but can't cross from one to the other. And now I'll give a hint towards where are we going. This is the beginning of treatment of an electron in field theory. What did I do here actually? I went from a scalar field to a field with two components. Now, for an electron, we'll see, and that would be the Dirac equation, that I have to move to a field with four components. Why? And that we will prove here. With less components, you can't get special relativity. We are forced, if we want the minimal model that will be invariant under Lorentz transformation, we'll need four components in our field. We'll see it. These four components are 2 for charge and 2 for spin. So as a package deal, we'll get, at the end of the day, charge, positive and negative electrons out of it. And we'll get spin as an added benefit without to put it into them. And all that comes out from the requirement that Lorentz invariance will be kept. Now, it's of course a few steps ahead, but 2 components already give you the charge component. We can't see it because we have no electric field at the moment. Okay, I want to show that I could get this charge conservation from a different way of thinking. And that has to do with symmetry. So I have here the 2 components of the field. I want to do a transformation. One, I'm allowed. And theta is just a scalar, and this type of transformation is known as a global transformation. Why it's global? Because each point x is I'm multiplying it by the same phase. And now I want to show you that this Lagrangian doesn't change at all because of this transformation. Okay. Okay, so I'm writing down the Lagrangian. You can start screaming, 1 minute, we add 3 terms. Why are you writing down here only 2 terms?
It's not 2, it's...
Because mu would be in the same meaning that we have in general, in special relativity. 0 is time, 1 is x. And actually, at this point, I already can be completely general. Mu could be also 1, 2, 3, and so forth, because it has nothing to do with our original model that was one-dimensional. This symmetry is general for any dimension. So that's the way to write down the fields that we have written previously for any dimension, where mu equals 0 is time, and x, y, z, and whatever additional components I have are this mu. Okay, so let's put in the transformation that we did and see what happens to L. So just for me to be consistent, I wrote it with a minus here and a plus here. It doesn't change anything with this. Okay, and since
You wrote twice minus on the I.
yeah, because here I have the dagger outside. Here I already put the dagger
Okay,
inside,
yeah.
so here it's.
Okay.
And this is as trivial as can be, because e to the power I theta or minus I theta is just a constant. The derivatives don't play any role here. And I end up with the same result that I had previously. The fact that I put in this phase didn't change anything in my Lagrange. Or another way to say it, Okay, now we'll use this game just to show you how do you pull out conservation row out of the Nether theorem, just because it's the simplest and most transparent way to see it here. And now R is just with a dagger and without a dagger. Those are the two components of the fields that I have here. Okay, so all I did here is basically writing down the derivative.
Yeah, but why is the... I mean, the first is because partial derivative, yes?
Yes, and
the second one, why is it?
Because I have the Lagrangian depends on
Okay.
on both of them. And pay attention, here I have actually two or d plus 1 components. And R is with dagger and without dagger. It's much longer than written here. It's only under the summation agreement. Writing down all the... Okay. What else do I know? Someone can tell me from which hat did I pull out this connection? Exactly. That's our good old friend Euler-Lagrange. Okay. So I can take this expression, put it in here, and see what I get. So up to here, basically I just copied this definition into here. Nothing more, just to raise. Okay, it looks complicated, but really isn't. Okay, so this thing is just copied here. Okay? What did I do here? I put in this guy into the derivative. So now I'm doing the derivative of x mu over the guy that was here and the guy that was outside. And then I subtract the additional terms that I get because of this, which is this guy. And why am I doing it? Because of the simple reason that this guy and this guy are the same. So I can get rid of them. So I'm left only with this term.
Just why does it say?
Why are they the same?
It doesn't matter the order of the derivative.
Well, this guy is the same as this guy and this
But the
guy.
second term. Yeah, what you pointed. It's because that you can. It doesn't matter the order.
Right. Okay. Now the only thing I
Ah, okay, sure.
if I would write instead of these long terms just A and B, it would be trivial. Just because it's long, but not. I do here nothing. I just pull this term inside into the derivative and subtract the additional term that I get because of it. That's all. So I'll write it here. I'm just copying, not doing anything at this. This is equal 0 because it doesn't depend on theta. So I identified here what is another current. Okay. that's the conserved charge in the Noether theory. So let's see, according to what appears here, what is this conserved charge? So I'm just writing down the components. All I did here is just write down the Lagrangian. Wrote this term and wrote the Lagrangian. I am doing it because I would like to go and calculate it directly. Have only one place that I depend on phi here, and the derivative of phi. Okay. Second term. Just by the definition of the dependence of phi on theta. So now take all of it and put it into the definition. Yes.
שאלה קטנה. המיו בשורה הראשונה שם, אחרי השווה, המיו לא אמור להיות למטה?
יכול להיות, I'm not very pedantic on keeping the core and
אני עדיין לא יודעת מה זה אומר כל כך למעלה ולמטה, אבל...
It does, here actually it doesn't matter at all.
doesn't matter?
Doesn't matter.
Easy enough.
If it's easier for you to write them all.
תודה רבה.
And some of you should recognize it from the beginning of quantum mechanics.
Angular momentum.
No, much simpler.
It's similar to the tensor electromagnetic.
Guys, for the last hour, we're always going to the most complicated thing when it's really the simplest. The current of a wave function, phi complex conjugate derivative phi minus phi, that's the current operator in the regular quantum mechanics. Remind you, let's use psi, so we J operator. To an I that I never remember if it's the correct sign or the other way around. That's a current operator that you run into, perhaps even in modern physics, but sure in the beginning of quantum mechanics. Same structure. Okay, and then I can take J0, gets a definition of Q, all's good. So that's connection between symmetry and conservation. Okay, we'll start, probably we won't finish. I want to get to something much more surprising. And that would be to show you that basically, I talked about that I'm missing here some coupling to some other field in order to get dynamics. And I told you that symmetry can give me some interesting conservation laws. Okay, I want to go to this type of field, the complex field, and demand a stronger type of symmetry. What do I mean by a stronger type of symmetry?
So the symmetry here was the change of phase?
Yes.
Okay.
And now I come and I add one small change here in the symmetry.
It's not global.
It's not global. I want to change the phase in a different way at each given point of time and space. Okay, check me at home, but if I'll stick it into this Lagrangian, of course, it's not symmetric. Okay, and here we have some change in the way that we're thinking about how do we get physical results or understand the physics of a system. basically, of course, it was created the other way around. We wrote a Lagrangian, saw that it fulfills this symmetry, and said that's a very interesting symmetry of nature. But let's present it the other way around. I'm coming and telling you, look, nature has to obey this symmetry. Why? I had a vision that told me. Now I have to write a Lagrangian that will fulfill it. Okay. With only these phi's at hand, I can't do it. It's just not a symmetry that is obeyed in this Lagrangian. So I'm telling myself, okay, since I'm convinced for some reason that this is the basic symmetry of the universe, I'm probably writing the wrong Lagrangian, and I have to add an additional field to this game, because otherwise I can't fulfill this demand for symmetry. And the additional field would be just a 4 vector that behaves in the following way. Same way that this guy is transformed to this guy is transformed to this guy.
Theta is local.
A is a field with 4 components.
Theta is local.
Is local,
Derivative.
yes. It has a derivative here. If it wouldn't have been local,
Been
so
zero.
transformation has no meaning. Okay. And basically, if I have this guy, I'm able to write down a Lagrangian that will conserve the symmetry. And here, just for completeness, I'll add a Q here, just a number, scalar. And moment, another definition. So what did I do here? I took something similar to this Lagrangian, made some changes. The derivatives are not defined in a similar way to, well, they're similar, but not identical. Okay, this is this term and this term. Here, nothing changed. And I added an additional term. Now, let's look actually what happened here. I have here one term that depends only on phi and phi bigger. Okay? This term actually doesn't care what type of thing, how I torture the phase here, because it's the field times the complex conjugate. Whatever I do to the phase doesn't matter. Therefore, it remains the same. Nothing changed here. I've added a new field. In parentheses, it means I added a new particle. And if I wouldn't have my original field, this is how this additional field behaves if phi is not present. It doesn't depend on phi. It depends on derivatives of A, which is my new field. So for this new field, this is the non-interacting term. Why is it such a structure? We'll understand. Probably not in this lecture, in the next one. And here I have basically a multiplication, a bit complicated, of the A field and the phi field. That is basically interactions between two different particles. And basically what I have here, and let's see if someone of you remember something about analytic mechanics. What does this term remind you? Nothing? Excuse me? Yes, but of what system? What system looks exactly in this way? This is actually an electromagnetic field. So I suggest before next lecture, well, actually you had it in, I think in one of the tutorials, writing down the Lagrangian of an electromagnetic field. This is a free field, electromagnetic field, and this is a connection between a particle in a free field. So now I can look at it from two different directions. One is a more natural one, which is saying, well, I know this Lagrangian from where? I know it from classical electromagnetic. If I put a particle with charge Q into a field, electromagnetic field, and want to write down the Lagrangian, the classical Lagrangian, that is the way that it looks like. Okay, and then I say, well, you know what? This Lagrangian fulfills a very interesting symmetry known as gauge symmetry. I can change the phase locally at each point, and I'll still have the same Lagrangian. I can look on it from the other way around. Tell myself, look, nature has to obey this gauge symmetry, and therefore it forces me to put a charged particle and an electromagnetic field in this structure. Otherwise, it can't fulfill the symmetry. And in modern particle physics, this language is very popular. You come and say, I get QED because I have to fulfill gauge symmetry. What is the difference between QED and what I've written here? The only difference is that QED is with electrons, meaning that I have to have here a 4 field, not a 2 field. But the structure is the same. I took the simpler case with only, because if you're thinking the phi field is actually bosonic, not fermionic. We'll talk about it in one of the coming lectures, but you know what is the basic difference between bosons and fermions? Anyone? Hmm? In a state, here I have no limit on a given k. I can have 0, 1, 2, 3. It's a boson. A boson is not an electron. But okay, so that's some charged boson. But the structure is the same. Now, what remains to be done? We have to go and show that actually when I'm doing these transformations, indeed the Lagrangian is invariant. And well, that we'll do in the next lecture. What I want to do here just is a small matter of definition. Just instead of writing this whole thing each time, it's sometimes written d mu and d. And here you get the first clue. I think the ones that didn't like up and down left. Am I right? But here you see some difference in the plus and minus I in those two. Just a way to remember in notation. Okay, so what did we do up to here? We saw symmetry. We understood a very simple case, which is a complex field with nothing else. so that something is conserved, the number of particles in the first component and the second component of the field. We went to a much more ambitious symmetry, claimed that this symmetry is obeyed by this Lagrangian, didn't prove it yet, we'll do it in the first part of the next lecture. And we got a structure out of it, which my claim, I didn't prove it, but the claim is you have to have this structure in order to obey this symmetry. And I got out of it basically forces in nature, because electromagnetic fields are forces. So I got here these A's, which are bosons that we know as photons, and we got the first time that we have two fields interacting with each other. Okay, I think we'll stop here. Questions? Okay.
Thank you.
נשמע, אני חייב לחסד שם.
לא, אתה יודע איזה ארוך זה?
כן,
זה נראה ככה. כזה, מטורף. יש כזה כאילו נשמע חומרים.
כאילו.
שמע,